We are given f of x and asked to find f prime of x using a logarithmic differentiation. Let's first rewrite the function and replace f of x with y. This gives us y equals the product of x cubed and the fifth power of x minus 9 divided by the sixth power of x squared plus 7. And now we will take the natural log of both sides of the equation. And now we will use the properties of logarithms to expand the right side of the equation. Let's first deal with the quotient. And since the natural log of x divided by y is equal to natural log x minus natural log y, on the right we will have the natural log of the numerator minus the natural log of the denominator. So again, we have natural log y equals natural log of the numerator, which is x cubed times the fifth power of x minus 9, and then minus the natural log of the denominator, which is the sixth power of x squared plus 7. And now we can expand natural log of x cubed times the fifth power of x minus 9 by using the product property of logarithms, where the natural log of x times y is equal to natural log x plus natural log y, which means you can write natural log of x cubed times the fifth power of x minus 9 as natural log of x cubed plus natural log of the fifth power of x minus 9. And we can expand one more time by using the power property of logarithms, which is natural log of x to the power of y is equal to y times natural log x. So applying the power property of logs, we have natural log y is equal to natural log of x cubed is equal to 3 times natural log x plus the natural log of the fifth power of x minus 9 is equal to 5 times natural log of the quantity x minus 9. And then we have minus natural log of the sixth power of x squared plus 7 is equal to 6 times natural log of the quantity x squared plus 7. And now for the next step, we will differentiate both sides of the equation with respect to x. On the left, the derivative of natural log y with respect to x requires a chain rule. The derivative is equal to 1 divided by y times dy dx. Again, we're differentiating with respect to x, and because we have a y term, we have this extra factor of dy dx due to the chain rule. And then equals on the right, the derivative of 3 natural log x with respect to x is equal to 3 times the derivative of natural log x, which is 1 divided by x, and then plus the derivative of 5 times natural log of the quantity x minus 9. If we're not sure if we need to apply the chain rule, we're never wrong to apply it. Notice in this case, the inner function u is x minus 9. And since u prime is equal to 1, the chain rule is not required. The derivative is equal to 5 times 1 divided by the quantity x minus 9. And then we have minus the derivative of 6 times natural log of the quantity x squared plus 7. Here we are required to use a chain rule, where u is equal to x squared plus 7. The derivative is equal to 6 times the derivative of natural log of the quantity x squared plus 7, which is equal to 1 divided by the quantity x squared plus 7 times u prime, which is the derivative of x squared plus 7 with respect to x, which is 2x. Let's go and simplify these products. We have 1 divided by y times dy dx equals 3 divided by x plus 5 divided by the quantity x minus 9 minus, in the numerator here we have 12x divided by the quantity x squared plus 7. The next step is to solve the equation for dy dx by multiplying both sides of the equation by y. Let's do this on the next slide. So again, now to solve for dy dx, we will multiply both sides of the equation by y. On the left, y times 1 divided by y simplifies to 1, leaving us with dy dx equals, on the right, we want to have the derivative in terms of x, not x and y. So now we'll replace y with the original function, which is the product of x cubed and the fifth power of x minus 9 divided by the sixth power of x squared plus 7. And of course we have times 3 divided by x plus 5 divided by the quantity x minus 9 minus 12x divided by the quantity x squared plus 7. So we probably could leave the derivative in this form here, but let's go ahead and clear the parentheses by distributing. We have dy dx equals, for this first product, notice one factor of x will simplify out between the numerator and denominator, and therefore the product is going to be 3x squared times the fifth power of x minus 9, all divided by the sixth power of x squared plus 7. And then notice for the second product, one factor of x minus 9 between the numerator and denominator will simplify out, leaving us with plus 5x cubed times the quantity x minus 9 to the fourth, divided by the sixth power of x squared plus 7. And then minus for the last product, nothing will simplify out. Multiplying, we have 12x to the fourth times the fifth power of x minus 9, all divided by the seventh power of x squared plus 7. And now looking at the fraction, notice how the first two fractions do have the same denominator. So let's go ahead and combine those two fractions. We have dy dx, or we'll call it f prime of x now, because that's what the question asked for, is equal to, again, combining the first two fractions, we know the denominator is going to be the sixth power of x squared plus 7, and the numerator is going to be 3x squared times the fifth power of x minus 9 plus 5x cubed times the fourth power of x minus 9, and then we have minus 12x to the fourth times the quantity x minus 9 to the fifth, all divided by the seventh power of x squared plus 7. And we'll go ahead and leave the derivative function in this form here. But again, we probably would have been fine by leaving the derivative in this form here. I hope you found this helpful.